Good day everyone. So today in this video we are going to be looking at reflection at a curved mirror. So in our last video we talked about reflection on plane surface, that is plane mirror. So now reflection at a curved mirror, we have two types of curved mirror. We have the concave or converging mirror, and we have the convex or diverging mirror. So these are the two types of mirror we have. Now in the concave or converging mirror, how does it look like? Now the concave mirror is this. So say we have curved mirror. So for a concave mirror, the reflecting surface is shiny. That is, we polish the reflecting surface. So this side is the reflecting surface. So if I shade this side, this is the blunt side of the mirror. That means the reflecting surface curved inward. So it's curved inward. So this is the reflecting surface. So beside this one is concave. While for the convex mirror, we have something like this. But instead, this side is the reflecting surface. So this place is blunt. Nothing is there. So essentially, maybe in our everyday life, we might have come across these two. So we are going to be looking at the properties of this mirror and how images are said to be formed on these types of mirror. So let's start with the converging mirror, concave mirror. So images formed by concave mirrors. Now, if we have a concave mirror, let's say these are a concave mirror. So that means this side is the reflecting surface. So we have what we call the pole. The pole is the center of the mirror. Then we assume a line that passes through the pole. We assume the line. So this line just assume, it doesn't exist. So this line is what we call the principal axis. So this line is the principal axis. Then we have a distance from P to this we call F. So this F is called the principal focus, while the distance between the pole and this is called this F, which is the focal length. So F, principal focus, and this F here, the distance between them is the focal length. Then at this point here, we have what we call the center of curvature. The center of curvature. So this center of curvature is just the midpoint of a sphere. So you know, for us to have a curved mirror this way, we have to first have a sphere. So this is a sphere. So when we cut this sphere into two, you can see this part we have a curve here. So let's say this is the mirror. So this is if I draw something like this and this. So essentially what I'm saying is that this is the pole and this place is C, which is center, the center of that sphere, of which this curve is part of the sphere. So this is our center of curvature. Now you can see that from here to here we can call it what? Radius. So actually it's the same here. From here to this pole we call it R. And R is what we call the radius of curvature. Now the distance from here to here is same as the distance from here to here. So therefore we can say R, or we can say F, that is this, F is equals to R, that is the radius over 2, or we can say R is equals to 2F. So if you look at that, now we want to say how rays, light rays, they fall when they fall on this mirror, how they are formed. So let's say we have rays of light coming this way and they hit this way. Let me use two rays. So if these are rays of light and they fall on the reflecting surface of this mirror, so how will they be formed on all these things I draw here? So when this ray hits this mirror, it's going to be reflected. So when it is reflected, it's going to fall on this principal focus. So that is all rays that are parallel. You can see this line, they are parallel to the principal axis. So they fall on the principal focus after reflection. So after reflection, they tend to fall on this principal focus. So this one will also fall on this principal focus. So that's the rule. All rays that are parallel to the principal axis, they tend to fall on the principal focus. So this is how rays of light fall on concave mirror. But essentially we have the same thing for the convex mirror. So that's for concave. Now for the convex mirror, we have something like this. So we said this plate part is the shaded part, then this is the reflecting surface. So we have F and we have C. So we can also have this F and C at this place. So from here now, if we have rays that are parallel this way, let me use two rays of light. We said they will fall on the principal axis. Now, why do we call this a converging mirror? Is because after the rays after reflection, they tend to converge at this point. So they converge at this point. That's why we call it a converging mirror. But for this, the rays will diverge. So they will diverge and they will be formed at the back here. The rays, they will always be formed at the back here. So they will diverge. So when this one comes this way, it diverges this way. This one too, when it comes this way, is going to diverge this way. So they tend to what? Diverge. So that's why we call them diverging mirror. So next we are going to look at how images are formed when we place objects in front of these mirrors. So starting with the concave mirror. So the first one we have is object so we want to look at the properties of the image that will be formed when we place an object between F and P. So we know what F is. F is the principal focus and P is the pole of the mirror. So I'll have my concave mirror here. So I have this is the principal axis. I will say this place is the pole. So we can choose any convenient distance from the pole to F. Right? So this is our focal principal focus. Then we can have, so the distance between this and the distance between this should be the same. So we have C to be on this point. So we said our object is between F and P. So between F and P, so it can be anywhere in this region. So if I place an object, let's say this is the object, let me call it object O. Now from the rule is that this light is going to reflect on this object in this direction. So let's say this is the ray of light in this direction. So we said all rays parallel to the principal axis, they tend to fall on the principal focus. So this is going to reflect this way. So it's going to fall on F. Then, after doing this, we are going to draw this. From the top of the object, we are going to have another ray this way, will fall on C. So wherever this line, these two lines, where they converge, of course you can see they can never converge here. This line is diverging. But what about forward this way? So if I continue this line this way, and this one continues this way. So sorry about the diagram. I'm not using the drawing instruments. That's why it looks this way. But let's try to understand the main principle behind it. So this, they will converge this place. So when we draw, we are going to draw an arrow with the arrow pointing at where they converge. So that's where our image is formed. So the image is formed this way. Okay, let's indicate this by, so that I will not be confused. So this shows that this is the reflective surface. Now, let's look at the properties of this image that is formed now. Now, the first question that will be in your mind is that why is the image, why is it formed here? Why is it not formed here? Now, any image that is formed here, you can see, we said this is the front of the mirror. So this is the back of the mirror. So the first property we have, property 1, is that the image is formed behind the mirror. So the image is formed behind the mirror. Another property is that you can see the object. Look at the size of this object and look at the size of this image. Now you can see that the image is larger than the object. So that property is what we call magnified. So the image is magnified. Now, another property, whenever an image is formed at the back of a mirror, we said it is virtual. So we have a virtual image is produced at the back. Then another thing is the image is erect, or we can just say is upright. So you can see it's standing right, parallel to the object. So these are the properties of the image formed when an object is placed between F and P. Now let's look at when this object is placed between C and F. So object between C and F. Now another thing is that the distance from here to here, any point, if I'm to measure the distance from here to here, is what we call the aperture. How open is the mirror? So I have my P, F, and C. So our object is between C and F. So if this is the object, so a ray of light will pass this way in this direction. Then it will be reflected onto the principal focus in this direction. Then we said from the top of the object, we are going to have a ray falling onto C. This way. I think that diagram. Okay. So you can see where the convergence is. They converge at this point. So I'm going to draw a straight line onto this with the arrow facing this way. So this is the image that is produced, and this is the object. So let's look at the properties of the image that is being produced. This is the image. First thing is that the image is formed in front of the mirror. So image formed in front of the mirror. So whenever image is in front of the mirror, we'll say it is real. So the image is real. So in contrast to real is what? Virtual. That's opposite. Opposite of real is virtual. So you can see the image is in front of the mirror. Then another thing, you can see the image is larger than the object. So we say it is magnified. Then, but look at the arrows. You can see the image, the arrow is pointing down. While for this, it is pointing up. So what can we say about this? So we say it is inverted. So the image form is inverted. So you can do the practical. Take a concave mirror, then just change as you are moving further away from the mirror. You are going to see that the image will become upside down. That's inverted. Now, this is only where the image is upright. For any concave mirror, the image is only upright whenever the object is between F and P. That's when you have upright. So when we draw different rays, you are going to see that. The next one we're going to look at is object placed at F. Object at F. So when we have curved mirror this way, so this is the principal axis. So I have F and this is C. Now we want to look at object placed at F. So I'm going to have a ray in this direction, then it will be reflected this way. Then from this, let me put my C. So draw something like this. Now, as you can see, these two lines, they can never meet, either from this side or this side. They will never meet, so they are parallel lines. So what we say here is that one, the object form is, the image is formed at infinity. So image is at infinity. Then 2, we have that the image is always magnified. So the image is magnified, that is, it must be larger than the object. So that's the properties for when the image is placed at F. That was number is 3 and is 4. Now let's say image object at C, center of curvature. So object is placed this way. So it will reflect. Now remember our C supposed to draw from the image to this, right? So it will just be this. So from C to the image, so we have this. So remember, we can have multiple reflection of light. We have light going through this direction also. So all they will meet at this point. So our object is formed at this place. So object is placed at C. So if you are to use your ruler and using a particular measurement, you are going to find out that one property is that the image is formed at the front. So let's use real. So the image is real. 2, the image formed, you can see, is inverted. So we have inverted image. So this is the image formed, and we have this as the object. So it's inverted. Then 3, is it magnified? So no, the image is what? Same. So image is same size as object. So the image size doesn't change. So those are the properties of this. Then you can also add that the image, where the image is formed, the image is formed at C. So object placed at C, image is also formed at C. So let's look at when an object is placed beyond C. When we say beyond C, that means anywhere in this region. So if I have objects this way, so it will fall on F this way. Then from C to the top of the object, we are going to have a wave going this way. So where they meet, where these two lines intersect, so we have our object placed there, and the arrow will be this way, in this direction. So we have the object here, and we have the image formed here. So let's look at the properties of this image. So one, the properties. If you look at this image, it's formed in front of the mirror. So the image formed is real. Now, the image formed, look at the arrow is pointing down, and for the object is pointing up. So say it is inverted. Now, what happens to the size of this image? You can see the image is smaller than the object, so you can write image is smaller than the object, or you can just say the opposite of magnified, which is diminished. So the object is diminished. Then what else do we have? Where is the object? Where is the image formed? So the image is formed between, so you can see the image is formed between C and F. Then what other properties do we have? So I think that's all for that. So essentially those are the properties. Those are the various positions we can have image. Now, so, and I said in the beginning that the only place where you have the virtual image form is when the object is between P and F. That's the first diagram we drew, where we have the image between P and F, and that's the only place where you have an upright image. So if you want an object to be upright, that is, it is not inverted, the only position where the image should be is between the principal focus and the pole. That's the only region where you can have the upright image as well as a virtual image. So let's now look at the image formed by a convex mirror. Now, objects that are placed in front of a convex mirror. So let's choose any position. Let's say the object is placed at this place O. Now, so this is the pole. For this, we are going to have F here, we are going to have C here. Then, when rays of light strike this mirror, it turns this way. So remember, we said it's going to fall on. So let me use the dotted line since it is formed at the back of the mirror. Then we are going to have from C to the top of the object. So I'm going to draw something like this. So from C to the top of the object. So where these two lines meet, this place. So wherever the object is, if you place it beyond this part or you place it here, these are the only properties of convex or diverging mirror we have. One, you see that the image is formed at the back of the mirror, so image is virtual. Two, the image is smaller than the object, so we'll say it is diminished. Three, it is what? Upright. Standing upright. Or we can say it what? Erect. So those are the properties of image formed by a convex mirror. Then the next thing we are going to look at are the uses of this mirror. So the uses of curved mirrors. So we'll start with the concave. Now for the concave mirror, they are used as dentist mirror or shaving mirror. So dentist or shaving mirror. So they are used in astronomical studies and for focusing radiant heat. So that's for concave. Then for the convex mirror, what are they used for? So for convex mirror, they are mostly used in vehicle side mirror or rear mirror. So you can, some people took the driving mirror as a plane mirror. So no, they are not plane mirror, they are curved mirror. So you can touch, when you get to your car, you can touch the mirror and see whether is it plane or is it curved. And the type of mirror used there is convex. So convex mirror is used as a driving mirror. So you can always check, and the reason why it is said that object in the mirror looks closer than they appear to. So you can find out that. And once you get the answer, you should comment it below in the comment box. So thank you very much. Make sure you like this video and you should subscribe. Also, if you have any questions, you can put it up in the comments box below. So thank you very much. And ensure to click on the ring button for more notifications.